Earlier, we learned how to use backward regression to select a model, and that was all based on p-values. So you take the largest p-value, remove that variable from the model, and keep going with that process one at a time until all of the variables that are left are statistically significant. But this is all based on p-values, right? And in this class, we spent a lot of time talking about all the problems that can come up with p-values, one of them being that if your sample size is large enough, you can end up with small p-values even if the variables aren't actually adding that much in terms of variability explained. So in this video, we're going to talk about an option that pays more attention to R-squared that's called best subsets. So I'm going to go back to the same best value colleges data set that we used earlier. And I'm going to start off the same way, analyze fit model, because I'm going to consider more than one explanatory variable. And I'm trying to predict average salary. And I'm going to start with all the same explanatory variables. So I've got admittance rate, 4-year graduation rate, total cost in state, total cost out of state. And I'm going to put all of that in my model effects. But then for this one, I'm going to change the personality up here. So instead of standard least squares, I'm going to pick the stepwise option. And then I'll click run. And then at this next step, I'm going to click the little red arrow next to stepwise, and I'm going to choose all possible models. So I want to consider basically all possible combinations of these 4 explanatory variables to see which ones are best. So I'm going to start off with 4, so that means that I can have up to 4 explanatory variables in the model. But then I only actually want to see the best one of each size. So I'm going to change this number to 1. And I'll click OK. So this is showing me 4 different models that I can use, and it's showing me specifically the best model in terms of R-squared for each of the sizes. So looking at this output, I can see that the best model with 1 predictor is the one that uses out-of-state costs. So if I have to use only 1 predictor to predict average salary, then I would want to use out-of-state cost. And the R-squared for that is 0.35, so it's explaining about 35% of the variability just with that 1 explanatory variable. And I can also see what my root mean square error is, so that's giving me a sense of how large the residuals are, right? We would be on average off by about $5,798 in terms of the average salary for that university. So looking at the second row there, we can see the best model that has 2 explanatory variables. Still has out-of-state costs, but now we're also adding admittance rate, and this makes a pretty big difference. So adding admittance rate, I have 2 T's. That doesn't look good. I don't know. Admittance rate makes a big difference. Right, because R-squared for the 1 variable model was 0.3527, and then adding an admittance rate, the 2 variable model was 0.4597. So we're going up like 10%, a little over 10% in terms of the variability explained. So that makes a big difference. Adding in that variable explains a lot more of the variability in average salary. But after that, if we look at the changes in R-squared for the models that come later, after that, changes in R-squared are pretty small. So this is obviously subjective, right? If we're thinking about how big is the change in R-squared, you know, going up from 0.4597 to 0.4657, that's, you know, less than 1%. Is it worth it to add another variable to the model? That's kind of a subjective decision. I think it would be reasonable to cut it off at 2 just because it seems like those changes are pretty small, but also you could make an argument for stopping at different places. From 3 to 4, I mean, that's very small. 0.0002 is the increase in R-squared, so it's probably not worth it to include both in-state cost and out-of-state cost. That really seems redundant. So in this case, using best subsets, I think picking the 2 variable model with admittance rate and total cost per year out of state, that would be a pretty reasonable model choice, and that's also the same one that we got from backward selection. So sometimes they'll be consistent with each other. Other times they won't. Other times you might pick something totally different based on best subsets than you would with backward selection. And one more thing I wanted to note while we're here, notice that the R squared only goes up as we add more variables to the model. So by the end, it's only going up by tiny increments because adding that new variable doesn't make much of a difference, but R squared cannot go down. There's no way that you can add a new variable and suddenly explain less of the variability. Root mean square error, it seems like root mean square error could only go down because we've been interpreting it as the size of the residuals, and that's a reasonable interpretation, sort of an intuitive interpretation, but now's a good time for me to mention that that's not technically true, because remember, the denominator in our mean square error is actually the degrees of freedom, not the sample size. So it's not exactly a regular average where you would get like the average size of the residuals. And so it is actually possible for the root mean square error to go back up, because if you're adding another predictor, then that's making your denominator smaller because you're doing n minus 1 minus p, and that can end up making your root mean square error bigger. So I still think it's fine for us to continue interpreting root mean square error as we have been. Intuitively, I think it makes a lot of sense to interpret it that way, but it's also good to be familiar with how that value is actually calculated.